Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Professor Ross served as a chair professor in CS in Polytechnical University from January 2003. Previously, he has been a full professor at the Eurocom Institute for 5 years and at the University of Pennsylvania for 12 years. He received his PhD from the University of Michigan. Professor Ross has a lot of interest, including peer-to-peer file systems, internet measurement, video streaming, web caching, and all the other things. He is an associate editor for IEEE Transaction on networking right now and has served on numerous journal editorial board and conference program committees. He has been an advisor to the FTC on peer-to-peer file sharing. Professor Ross is also a co-author of the popular textbook, Computer Networking, a top-down approach featuring the Internet. And he has been the founder and the CEO of Wimba, an Internet startup which continuously develop and market Java-based asynchronous and synchronous VoIP technologies. Without further ado, let's have Professor Ross to deliver his interesting talk.
Okay. Well, thank you. I hope you find it interesting. So thank you very much for inviting me here. It's been a great pleasure to visit Microsoft. This is my first time in Bellevue, and it's very exciting to be here. So today I want to talk about some of the work that we've been doing in our group at Polytechnic University in the area of P2P live streaming. We've been working in the P2P area now for a number of years, probably for over 4 years or so. But more recently, in the past 6 months or so, we've been focusing more and more of our attention on the live streaming problem. So, and by live streaming here, we're referring to video live streaming. So just before we get going, was looking at the Wall Street Journal today, and there's this, in the press, there's just more and more articles about video over the internet. There was an article on the front page of another newspaper yesterday, and in the Wall Street Journal, they talk about YouTube, which is a very popular video sharing site, and a couple of interesting statistics were presented in the article. One thing is that the YouTube site already has 6.1 million video clips there. And in fact, that number grew by 20% in the past month. So it's growing rapidly. People are, young people in particular, are adding video clips to that site at a rapid rate. The estimated amount of storage that's consumed by those video clips is 45 terabytes. So it's a significant amount of storage there. Just on Sunday alone, this past Sunday, just a few days ago, 1.73 billion views of videos took place on Sunday. And if you look at the amount of total viewing time since the beginning of YouTube, which was last year, not too long ago, there's been over 9,000 years so far of total viewing time by the people at large out there. So, what this is saying is that video, it's taken a long time. People have been talking about video over the internet for a long time, but it is finally here in a very big way. And it's probably going to be here even in a bigger way in the future. So, of course, YouTube is sort of video file sharing, video on demand. What we're going to look at, though, in today's talk is more on live video, and in particular on IP television. And so what's sort of long-run vision of IP television? The vision is that there's going to be thousands of channels, maybe 10,000s of channels out there available, television channels available to be viewed from the internet. And these channels will come from hundreds of different countries. And some of the channels will come from network television, highly produced, but others will come from independent artists, maybe individuals or small groups of people with small amounts of funding. Some may just be webcam videos. Some people might set up a webcam at some interesting location, and for whatever reason, hundreds or thousands of people may want to watch that all the time. It might be lectures and events. Conferences will be broadcast in professors' lectures, etc. Could be part of the channels. In the vision too, it's not hard. Right now we're seeing live streaming at 300, 500, even 800 kilobits per second. So it's not hard to imagine video coming in at rates of 1 megabit per second or more in the near future. And so in this vision, of course, each channel is going to be channels will be viewed by different numbers of users. Some may only be viewed by 10 users. Others may be viewed by 1 million simultaneous users. So this is sort of the vision. And one thing that we're interested in is how can we make this vision reality? So some of the challenges are, suppose you're a popular site, and you have some content that's very popular, a lot of people want to watch. How are you going to get that? Say maybe 1 million people want to watch it. How are you going to generate 1 million streams to 1 million different people at say 1 megabits per second or higher in some kind of cost-effective manner? And without using IP multicast, because IP multicast is just not widely deployed. So the natural solution, this is that a lot of people are thinking about. I can see a lot of people here at Microsoft are thinking about it now, is considering peer-to-peer distribution. Yes.
What are some of the reasons why multicast didn't really take off?
That's, I don't have a really good answer, but I think, part of the reason is that I've been told is ISPs don't make money from multicast, so there's no reason to, ISPs make money, more traffic the better. And so they necessarily don't make money. And then there's also a lot of issues of coordination problems among ISPs. So to get multicast to work, you have to get the ISPs to coordinate better, and and so that just hasn't happened. Still, someday maybe it will happen, but it's technically very feasible. It's more of a policy and economic issue why it hasn't happened. So, in the IP TV space, there has been some success stories. It's not widely discussed in the open press yet. It's pretty well known, though, in the academic and research communities. One thing is that one of the first success stories was this CoolStream coming out of Hong Kong 2 or 3 years back, and they were actually very much pioneers in this space because they were the first ones to develop widely deploy a system that's using a pool-based architecture that we'll get into. And they reported 4,000 simultaneous users in 2003. Now, what they did was they took television feeds and from I think actually North American feeds as well as Asian feeds, and made them available to people using this P2P network. Now, more recently, there's been a number of commercial products again coming from out of China, and there's many companies doing that now. But two of the more popular ones are PPlive and ppstream. Many Chinese Americans, particularly in research community, are very much aware of these deployments because what they do is they make Chinese television shows, which are in the Mandarin language, available to anyone that has an internet connection. So a lot of American Chinese people who want to watch Chinese television, very naturally, they can't do that because it's difficult to do that from North America. But now it's through the internet it becomes possible. So part of the talk today is about some of our measurement studies of one of these systems, that is PPlive, and we observed that, for example, just as one example, we did some measurements during the 2006 Chinese New Year celebration. And we found that there were, PPlive was supporting at that time over 200,000 users, which were receiving the video at rates varying between 400 and 800 kilobits per second, which corresponds to an aggregate bit rate of 100 gigabits per second. So a very significant aggregate rate. And this is, again, this may only be the tip of the iceberg of what's to come. Who knows? Another, a company that seems to be as popular as PPlive now is called ppstream, again from China. And they, as well as PPlive, broadcast the World Cup. And although we didn't measure that event, supposedly there was a huge amount of traffic for the World Cup as well. World Cup, Soccer Cup. So what are the challenges in IP? Some people refer to it as IPTV. Some people refer to it as P2P live streaming. We'll use both terminologies here. What are some of the challenges? Well, it's bandwidth intensive, obviously. We're talking about, we just saw an example of 100 gigabits per second. Obviously, peers come and go. So it's going to be P2P. We're going to do the distribution using a P2P infrastructure. And of course, one of the challenges in all P2P systems is that the peers come and go. We have asymmetric residential access. A lot of people throughout the world have some kind of ADSL connection, residential connection, where the upload rate is much lower than the download rate. One issue is one challenge is that most likely in the future we'll need to have some kind of incentive structure for redistribution. When a peer gets a video, that peer will need some form of incentive to redistribute that video to other peers. So we'll talk a little bit more about that later. Another issue that we're going to get into is lags among viewers. That in these P2P streaming systems, typically the viewers do not see the live video exactly at the same time. So for example, if you're watching a soccer match, one person might see the goal at one time, another person may see the goal 20, 30 seconds later. It's just a characteristic of these systems. And so one challenge is to reduce those lags. So if we want to have more, if we want to allow for some interactivity in the future where we can allow some uplink communication, obviously we're going to want to reduce those lags. Then there are issues of security as well that we won't talk about too much today. But Friday I'll be giving another talk, and we'll be talking only about security in that talk. So some architectures for P2P streaming. There are basically two classes of architectures out there. One's been out for a longer period of time, and one is that's push tree-based design. So in a push tree-based design, you set up this application-level multicast tree from the source to all the destinations, and you push the content, to all the receivers through the multicast tree. And there's been a number of designs for that. One that's discussed quite a bit is called N-System Multicast from Carnegie Mellon University, and that's you can go visit their webpage. They've used that for a number of events to reach out to people typically in the order of hundreds of receivers. These other systems that I referred to, PPlive, CoolStream, and ppstream, are pool mesh-based designs. And so what's meant by that is you don't set up an explicit multicast tree. Instead, it's much more like BitTorrent. These systems are very, very similar in many ways to the BitTorrent design for file distribution. And so basically in BitTorrent, well, we're going to, the idea is that a particular user grabs chunks from many, many different nodes and reassembles those nodes, those chunks into a video stream. But so it's like BitTorrent, but with live streaming. So we'll talk about that. So let's. So today's talk, now after giving this introduction, is really I'm going to talk about two papers. So as always, this is something I always do. I always try to cram too much into a talk, and I'm going to do that again today. But feel free to interrupt me at any time and ask any questions. And I think we'll be able to get through all this material though. The first part is reason this talk is called practice and theory is the first is a measurement study of PPlive, and this is joint work with a number of people at Polytechnic University, including Jian Liang, who is doing an internship here this summer, and he was very instrumental in this work here. He was the one that really sort of got us going initially in this particular measurement study. And so a short version of this paper has appeared at an IPTV workshop a few months ago, which was held jointly with the WWW conference. And we have an extended version on our websites. And the second part of the talk is having done this measurement study, what we did is we took a step back and we said, okay, what are some of sort of the fundamental ideas behind P2P streaming? Can we develop a model that's going to capture some of these ideas and expose the fundamental issues? So that's what I want to talk about in the second part of the talk. And again, that's joint work with some people at Polytechnic University as well. So, quick overview, a very high-level overview of how pull-driven, mesh-based P2P streaming works. So, first thing you do is you locate other peers watching the same channel. So this is very similar to what BitTorrent does. In the first step of BitTorrent, you need the user who wants to download a BitTorrent file needs to locate other users who are also downloading that file. And the same thing here. We need to locate the other users who are watching this particular channel. Once we determine a large number of users somehow, there's many ways you can do that. We'll talk about that in a second. Then you can establish TCP connections with all those or a subset of those users. So you can attempt to establish TCP connections. So you sort of create now you're creating now this graph overlay network with your TCP connections. Once you have those TCP connections, maybe you might have 50 in place. So you have 50 TCP connections with other users watching the same video. Then what you can do, the video, I should have mentioned here at the beginning, but the video at the source is divided up in chunks. And the chunks of the video are being distributed to all the different peers, similar to the way chunks are distributed in BitTorrent. So once you have these TCP connections in place, you can go and, just like in BitTorrent, you ask your neighbors what chunks they have. All right, and then then your neighbors will respond and tell you what chunks they have. And once you know what chunks your neighbors have, you go and request various chunks from your neighbors. Typically, of course, in a live streaming system, you're going to request chunks that need to be played out in the near future. You're not going to request chunks that are very far into the future. You're going to instead request chunks that need to be played out very soon. The other thing you're going to do, of course, is you're going to upload chunks to others. So because you're a consumer, you're getting chunks, but you're also going to redistribute those chunks as well. And finally, you're going to, as you receive the chunks, you will order them and feed the data to the media player for display. So that's basically the overview of how, in general, how all these systems work: CoolStreaming, PPlive, PPstream, and any other ones. But of course, there's our differences in the details. Now, PPlive locates peers in this manner here. They have, first step, what happens is a user over here, you contact a channel list server, which lists all the different channels that are available, that are being distributed by PPlive, and you select one. Once you select one, then you contact a root server, which will provide you with a list of peers that are currently or most likely watching that channel. Now, in BitTorrent, that would suffice. You would just take a list of 40 or 50 that BitTorrent gets. PPlive, for some reason, not sure exactly why, once it gets that list of peers, it goes out and contacts many of those peers on that list to get even more lists, because these guys all have, each of these guys maintain a list of peers that they know about that are watching the channel. So, you get your list here, and then you contact other peers for their list, and then you aggregate that together, and you get an even larger list. So that's the first step. Okay. Second step, as we said, is that then what you do is you set up TCP connections to a subset of those peers. Not all of them necessarily, but to some subset. And again, the PPlive and ppstream are proprietary protocols. So these observations that we're making here are through a protocol analysis, some basic packet sniffing that we've done, and protocol analysis, and we've learned these things. So after you do that, after you set up those TCP connections, you make a request for the buffer you send out requests to find out what chunks each of your neighboring peers have. And those neighboring peers respond with what's called a buffer map. Very similar idea to what's in BitTorrent here. And the buffer map, basically the information that's in the buffer map, first of all, so your neighbor says neighboring, suppose you're Alice and Bob is one of your neighbors. Bob is going to respond to you with a buffer map. Bob is going to tell you, you're Alice, Bob is going to tell Alice the first chunk that it has, it has all these chunks, right, Bob has, and Bob is going to identify the first chunk, and it's also going to identify, it's also going to say which subsequent chunks it has. And so the way it does that is that it sends just a string of bits with a 1 signifying that it has that chunk and a 0 signifying that it doesn't have that chunk. So Bob has this chunk here, which is indicated by the offset value that's sent, plus it has the next chunk, the next chunk, the next chunk. So 1, 2, 3, 4, 5, 6, 7 consecutive chunks. Then it's missing 3 chunks, and then has another one, etc. So once again, as what you do as a PPlive client, or as just a general client in these systems, is that you get these buffer maps from many different peers, and then from that information somehow you decide which chunks you're going to request from which peers. And of course, the exact algorithm that's used is proprietary. If you look at the CoolStreaming paper, however, they provide fairly explicitly the algorithm that they use for deciding the chunks. But we won't worry about that too much. The chunk size in these systems is typically in the order of 1 second of video, maybe a half a second of video to 1 second of video.
Can you give an indication about what algorithm they use to pick the chunks? Because that's crucial to the performance, right? What chunks you're going to request.
Yeah, you have, there's 2 big issues, and it's similar to BitTorrent. One is what chunks you're going to request, and also you're getting you're getting requests from other peers for chunks to redistribute. You need to decide which chunks you're going to redistribute first, what priority you're going to give to various users. So anyway, answering your question, the basic things that you're going to take into account there is 2 issues. One is the issue is that obviously you're going to request chunks that are going to be played back in the near future. So if you need some chunk that's going to needs to be played out very, very soon, you're obviously going to request that. So that's going to be the highest priority. Second thing is you're going to use this kind of in the CoolStreaming paper, and they borrowed the idea from BitTorrent of rarest chunk first. So you're going to give some priority to the rarer chunks. So you have you get this map of what chunks are available, and suppose you already have a fair amount of buffer there, so you don't have to worry about the near future too much. Then you can look further back a little bit and try to get the chunks that are for which there's the fewest copies. So this is exactly what BitTorrent does. And so it's going to be sort of a blend of those 2 ideas generally in your scheduling algorithm. Okay?
And how do you know which chunks have the fewest copies? Is there a central map somewhere?
Okay. Well, basically, you only know that from your 50 neighbors. So basically, that fewest is taken from your 50 neighbors. Exactly the same thing in BitTorrent. They do the same thing. Yeah. Okay. So, and then it's like once you do that, just all these peers now are trading chunks with each other, just like in BitTorrent here. So just put that picture up there. Now, way these systems, they usually use a built-in media player, like for example, a Microsoft Media Player. And so this is sort of the streaming engine here, which is receiving these chunks from the other peers. It puts them in a queue. And generally the way it works is once the engine has reached a threshold, once it has buffered a certain amount of content that's defined by a threshold, that's then at that point it launches the media player, and supplies the media player with essentially a URL. The URL then makes a HTTP request to the streaming engine, and then the streaming engine responds with the file in an HTTP response. So that's how the video display works. So our measurement methodologies involved two things here. One is active crawling, and the other is passive sniffing. So let me just talk about both of those very quickly here. So active crawling, what we did there was Jian and a number of other people. And, Jian sort of led this, but everyone's been involved in this. Built this crawler, which visits all the peers in a channel every minute. So, for a given channel, it first goes to that channel server, gets a list of IP addresses, and then starts visiting all those IP addresses and gets the list of IP addresses from all those IP addresses, and then just keeps on going recursively until we visit essentially all the peers watching a particular channel. And that can be done very, very quickly, and this thing gets relaunched every minute, though. And so we learn the IP addresses of all the active peers, and also what we obtain is the buffer maps from all the active peers. So every minute we go out there and ask for the buffer map from each active peer. So that's what the crawler does. So that's one of our measurement tools. The other measurement tool is just some passive sniffing. So what we did is we set up two nodes at a university campus, one node watching a popular channel, the other node watching a less popular channel. We wanted to get some measurement results for both popular channels and less popular channels. And we also set up two monitors in homes, one in Manhattan and the other one in a home in Brooklyn. So we had 4 monitors watching 2 channels at the same time. All of this was going on at the same time. And so the popular channel was being streamed at a rate of 340 kilobits per second, or the video rate, coding rate is 340 kilobits per second. The unpopular one, a little bit less, at 312 kilobits per second. And then we built a customized PPlive packet analysis tool so that when we grabbed all this PPlive data, we were able to process it efficiently and get the information we wanted. So what I'm going to do now is just very quickly, not as quickly as you want, but I'm going to just present some of the measurement results, which will give us some ideas of what's going on in some of these large-scale live streaming systems. So this is from the popular channel is called CCTV3, and what we're plotting here is time. So this is going on over a little over a week here: Saturday, Sunday, Monday, Tuesday, Wednesday, and we're looking here at the number of active peers for this popular channel. And what we this is not extremely surprising, because it's something you would expect to see even on regular television, and that is that at a certain hour of the day, every day of the week, people are watching television more often than other times. At other times, people are sleeping. So people are sleeping over here. Typically, these peaks are in the evening when people are at home. And turns out that most of these peaks are occurring in the evening in mainland China time here. So we're seeing this sort of repeated effect here going on and on. So one lesson to learn here, it's not necessarily something that's surprising, but what we see is that user behavior in terms of watching video on the internet is not that different necessarily than what you might expect in ordinary television distribution. Here's just a graph here. Like I said, we measured the Chinese New Year event. Huh? Yes.
Maybe a difference would be if it's global on a global scale, then you'd expect there to be
some more smoothing.
Yeah.
I guess we could expect that. I mean, I'm going to show some geographical information soon. We see that still most of the users are people watching this are still in mainland China, but still significant many others are in the United States and elsewhere. But yeah, you would expect that in the future. But right now we're still seeing, since I think it's still a preliminary, we're still at the beginning of this technology. We're still seeing a lot of localized users watching it from the same general area.
Schedule.
Right, so I was wondering, that's even in China, but maybe the people over here.
That's a good point too.
Is the Chinese television put better shows in the prime time of Chinese time.
Right.
So people would tend to watch more of those better programs during that time.
Right, exactly. So there's a distinction now between when the content is good and when the users are wanting to watch.
I would basically say when PPlive is mainly redistribution of TV channels, this behavior probably is more true because of the prime time TV scenario Li is mentioning. Nowadays, PPlive actually trying to circulate shows. So for example, if you have a TV series, you pack 10 TV series in the channel and circulate that, then the prime time effect probably will go away. Because, global user probably will join in anytime. Then global-wise, probably the statistics can change. Because of the content changes.
So I think that that brings up an interesting point too. Is that in traditional television, right, stations would reserve their best programs for the hour that's most convenient for people, which is 7 to 10 p.m. typically, right? But now, if people are watching that all over the world, you may repeat your best programs. You may change the way that you distribute your content, right, in an internet context. Something I haven't given any thought about, but it's interesting you brought it up here.
So a certain percentage of the clients act as repeaters, even when people are not watching them actively. Something like seeding a torrent and BitTorrent, even if you're not actively downloading anything.
Well, we believe that's the case. We don't have. Well, I'm going to get into it a little bit more. We don't have proof of that or exact statistics, but we believe that's to be true. Yeah. So Chinese New Year event. See, this is a popular channel, but we're seeing sort of at peak usage about between 2,000 and 2,500 users. Many more users for the Chinese New Year event, where, as I said before, it gets up to about 200,000 users. And this is plotted on a log scale versus hours here. And so you see that before the event started, you have a relatively small number of users watching these channels, maybe on the order of 1,000 or 2,000. And then when the event started, which is around this time here, at 8 o'clock or so, you're up to 200,000 users. And it pretty much stays constant until the event ends. The event ends over here, and then users drop off very quickly over here. So, and then it goes down there. Now, peer departures. We have. I'm just reporting a snapshot of many of the statistics that we have. Some of the more interesting graphs. What this is showing. So we looked at peer departures as well, and you're seeing here is that that we're seeing at certain times. We are seeing large numbers, these spikes in the number of departures, right? It's, so we're seeing here essentially at a little bit after 4 o'clock and 6 o'clock and 8 o'clock, and here sometime around 9 o'clock it appears. So what do you think that's due to? Why are these spikes in the departures here?
The show is over.
Yeah, sorry, yeah, very natural thing. Show is ending, right? People, people are, watching that show and then quitting the channel. Yeah. So there's some behavior of that sort. Now, geographic distribution, what we did here was we took, we're out there crawling the whole network, and we get all the IP addresses, and then we use various services there that map those IP addresses to geographic locations. And what we're seeing here is that most of the time, the large majority of the users are from Asia, China, most likely, so here. This is actually plotted at Eastern Standard Time, okay, these hours here. So we see that at, I believe that's true. Right. At, maybe, yeah, so at 8 o'clock in the morning, Eastern Standard Time, which I guess is about 8 p.m. in mainland China, we see that the vast majority of the users here are from Asia, with a small amount from North America, and black here is all other countries. Then later, at 8 p.m. Eastern Standard Time in the United States, now we have a significant fraction of users watching this from the United States, relatively small number of users watching it in Asia, and still a large number of users also watching it from other countries. It might be Europe or Australia or who knows where. Okay. Just some other statistics here. Sort of looked at the TCP partners, video TCP, the TCP partners that a given node has. So this is the popular channel at a campus and a popular channel at a home here. Let's look at this statistic here. We see that essentially 72% of the downloads, the download traffic here. These are nodes that are in a Brooklyn Polytechnic campus. 72% of the traffic was coming in for this one channel from Asia, okay, and 26% of it was coming in from North America, and 1.5% was coming in elsewhere. So basically, one of the issues we're trying to grapple with is does this particular deployment use some kind of locality or not? I don't think these results are conclusive yet. Maybe you can help me draw the conclusions here. But this is what we're seeing here. One thing is we're in North America and we're seeing 26% come from North America. We're seeing a large amount from Asia, but that may just be because that Asia just has so much available. And we're only seeing 1.5% from other places. So given that statistic, there may be some locality being taken into account in the design here. Now, it's funny that the upload traffic is very different. It's very odd, is that so 72% of the traffic that we're receiving comes from Asia, but 83% of the traffic that we're uploading to other users is going to North American IP addresses. So for whatever reason, our nodes in New York City, the majority of the data was coming from China, and the majority gets redistributed to North American nodes in this particular measurement study. Okay. This is an interesting statistic here. This shows here upload and download rates, again for the campus monitor for the popular channel. And so what we're downloading at, remember that the video rate is about 320 kilobits per second, I believe. So it's this value right here. So we're downloading continuously at 320 kilobits per second. There are moments when, unfortunately, we can't download at that rate, so we're downloading at a lower rate. This is in time over minutes. And then we go back up again, maybe up a little here, and continue like this. And now this here is our upload. So this is plotted on a log scale here. So we're downloading at a rate of 320 kilobits per second, but we're uploading at a rate that's on the order of 3 megabits or 4 megabits per second. So we're uploading at a rate that's more than 10 times larger than the download rate. So what are we seeing here? So this is a campus peer. So campus peer is very generous, right, and redistributing this video to many other peers most likely. We're only downloading at 300 kilobits per second, but we're uploading to a lot. And this goes back to your other question is are there nodes out there that are just like seeds in BitTorrent that are sitting out there and just helping the system out? It's very possible that a lot of people, students, whatever, have, are running this at, at their university or whatever, and they go home at night and they just leave it on or something and let it redistribute. They might watch it and then, won't bother to shut it off at night and let it redistribute as the day goes on. Who knows what people are doing? So that's what we're seeing. If you look at the same kind of plot now for the same channel, but at home. So this is based out of either Manhattan or Brooklyn. I can't remember which one. Again, what we're seeing here is we're downloading once again at that rate of roughly 300 kilobits per second or so. But we're uploading at a variable rate, and probably on average it's close to that 300 rate. So in this particular example, we're downloading traffic at 320 kilobits per second and also uploading it at a similar rate. And the reason why we can't upload much more than that is because these are ADSL connections which have limited capabilities for uploading.
So for this experiment, did you limit the download, the maximum download rate?
No. But again, it's different from BitTorrent because this is live streaming, so you cannot really download at a rate that's higher than the streaming rate. So BitTorrent, of course, can go and download at the maximum possible rate. One of the fundamental differences in live streaming is that you can't download at that faster. Yeah, can't download into the future. Right.
Yeah. Is there any tit for tat protocol going on?
What kind of tit for tat? To our knowledge, no. There is, again, we don't know the protocol exactly what they're doing, right? It's proprietary, but highly unlikely that there is much tit for tat going on there. That's an interesting question. You may want to bring that up, discuss that at the end of the talk a little bit. So yeah, let's come back to that. Yeah. One more of these graphs. This is again at home, and it's a less popular channel. And what we're seeing here is that the home is downloading at the rate of the video, roughly 300 kilobits per second. There's a point here where there's a gap where we download at a lower rate, but we're uploading at hardly any traffic at all. Hardly. If you look at add this traffic up, it's like epsilon-esque traffic, very little traffic. So what we're seeing here is that in this particular snapshot, the home is contributing very little. Now, if you look at, I don't have the one for the campus, but in the case of the campus, that's still contributing quite a bit of traffic for this less popular video. Here's an interesting graph, I think. What we're looking here we're looking at a campus node, so with a lot of bandwidth, high bandwidth connection, watching the popular channel. And what we're plotting here is the top here this is over minutes here, is the aggregate, the blue is the aggregate download rate. So on average, it's in the vicinity of 320 kilobits per second. We see it's fluctuating all over the place at this short time scale. And what we're plotting here is we ask ourselves, so we're getting this video. Now you might wonder, are you getting this video essentially from one other feed? Is there, are these pull-driven systems really very similar to push-driven systems in the end? In a push multicast system, you might most likely just get your video from one feed. So you ask yourself, are we going to get our video as well from one feed? And so we plot here the download rate from the top download session. So this is the rate that we're receiving from the neighbor that's giving us the most. So one neighbor is giving us the most, and what's the rate? At what rate is that neighbor giving us video? And we see that it's giving it at a significantly lower rate than the aggregate rate. So what this means is that even over short periods of time, we're downloading from many neighbors simultaneously. We're not drawing all the video from one neighbor in these systems. We are indeed drawing the video from many different neighbors. Yes?
Is this a single session or it's one of the top sessions at any given instance?
This is a single session. So basically what was done was to calculate the session that provided the most video and then plot that here. Yeah, yeah. So you see it's throughout, throughout the entire duration, it's contributing a significant amount, but it's not contributing all the traffic. Okay, so that was, yes?
Sorry, before you go on, can I ask some specific questions?
Sure.
Can you go back to the redundancy slide for the popular and unpopular movie event?
This one here, I think.
Yeah. I happen to use PPlive for my parents-in-law, basically for their viewing of TVs. And I noticed two things. One is for the popular channel, at least for my home, which is an ADSL connection with 3 megabit download and 700 something upload, which is pretty high bandwidth, I would assume. The popular, unpopular channels, quality is very low. If I look at this graph, it should show the quality should be pretty satisfactory because you actually have the bit rate.
Right. In this particular trace.
Yeah.
Right.
Did you watch the movie for this event, and what's the experience you are getting? I mean, do you basically observe good quality or relatively poor quality? A related question is, we've discussed this before. Basically, in PPlive system, classify some channels as popular channels and classify some channels as less popular channels. Mm-hmm. And the general indication is less popular channel has a lower quality than the popular channel. Mm-hmm. If generally, I mean, in all the systems, the user is all the user is doing the best in contributing. Right. And the bandwidth distribution is about equal from unpopular and popular channels. The thing should not happen. Basically, the unpopular channel should have about same quality as popular channels. Have you experienced this behavior of low quality in unpopular channels? Right. And what possibility, I mean, why this happens? This is first question. Sure. Can you go to the popular channels? I have a second question. Okay. For the popular channel, if I look at the upload here, the upload basically bandwidth is on the order of 400 to 500 kilobit per second and most for the home, right? For my home, I suppose should have a 700 kilobit per second upload. And what I notice is when I run this PPlive, the quality of my internet connection is very, very poor. Generally, it blocks out all of your traffic.
It blocks out all of your traffic?
Basically, all of, I mean,
your upload traffic?
Meaning I cannot do web browsing or those kind of things
at the same time.
At the same time, because I mean, PPlive being a streaming system. Right. One thing they want to get basically users' contribution. They don't institute a limit. Basically, they don't let you to set upload limit. Right. And somehow it seems to me it consumes all my bandwidth. But in your case, it seems you have plenty of bandwidth left.
Right, in this particular trace. So, I think this is I think that's a good. Yeah, okay. I'll let you finish.
So the basic second question is: do you experience a quality drop for other internet service during the watch of popular movie event?
Right. Well, I don't have as much anecdotal experience probably as you have, because I'm not a native Chinese speaker, so I don't watch this. I watched it a little bit just to get a general idea, but I wouldn't watch it, obviously. But from from what I hear from other people using the system, I hear a lot of things similar to what you're saying. I haven't heard about the PPlive system utilizing all the bandwidth, but it seems that's something that I'm sure it's often true. This is just one snapshot of one trace, and in this case, you're right. It doesn't look like we're using all the bandwidth. Maybe we're using half of it. Who knows? But I just so just for whatever reason, the demand here isn't for all of it. It seems it's only for half of it. If we go back here, you might ask, why is there really no demand? I mean, we are receiving the video. Why is there really no demand for it? One reason may be is that this particular node may be sort of at the tail end, in many ways, in some sense, of the distribution, so that it has a lag that's behind everyone else, or it's close to the back. And therefore, other users are not interested in this content here because it's already very dated content, and they prefer going up higher up in the distribution process.
I agree with you.
Yeah.
Probably this is because of scheduling algorithm, because we are in North America.
Right.
The content arrive here pretty late.
Right.
And in the neighborhood, there's just no one you can.
Exactly. No one is interested in the neighborhood of that for that content. Good possible.
Regarding the second question, I think I have an answer.
Okay.
I have experienced the same problems. Jin, do you happen to use Verizon DSL?
Yeah.
Okay. It's a problem with their system.
Okay.
And I've experienced the exact same issue with BitTorrent, for example, when you have more than 50 TCP connections outstanding. And it was a problem which took something like 2-3 weeks to debug. There was no final resolution. It's a combination of firmware on their modem and their routers. Okay. So the solution for me was to switch over to cable with almost the same stated bandwidth, but much better experience, where the other applications do not suffer from starvation when you have BitTorrent or PPlive, for example, going on.
Can we talk later in the basically after the meeting? The reason is we are developing similar systems. We certainly don't want our system to have a poor performance on users.
I also have heard that under Vista, they have prioritized I/O, so you can set an application to be lower priority. Then all the I/Os that this application do will be of lower. It will give away to other higher priority applications.
Yeah, you can do that.
And for your first question, Jin, about why small systems don't perform well, I'd like to delay that and come back to that in the second half of the talk.
I have a quick question.
Sure.
So what's the order of nodes in the less popular channel? Like approximately how many are there?
Good question. Let's see. I have a chart that might. That gives that. Let's see. These are all popular. Where's the less popular? No, I don't have that. I have that information, but I'm not plotting it here.
Is it like 10 or 100?
No, it's. If you just give me a second here. The number of nodes for the less popular channel at the peak is 120, and then in the valley it's about 4 or 5 nodes.
Okay, and then
Yeah.
my follow-up question is, do you run the campus nodes and the home nodes on the same channel at the same time?
Yes.
Right. Well, there's 2 channels. So
But
we,
do you run them both on the less popular one at the same time?
exactly.
So
Yeah.
are you worried at all that you're like biasing like the results by running a campus node at the same time? If there's only 5 nodes at all on the whole channel?
I guess I'm not sure if it was the statistics are at the right.
The nodes are monitored, right? They don't contribute. There are nodes. They're just monitoring. They don't contribute.
No, they contribute. My monitors are also PPlive nodes as well. Yeah, so they are contributing. Yeah. Yeah. But it's not clear, for example, if those measurements took place during the valley period when there were only 5 users, or during a peak period when there were 120 users. So
if there's any locality, right?
Right.
Then your nodes are pretty close to each other, so it's still affected. Even
Right.
with 120, you would expect like 80 to be in Asia and only a few to be in the New York City area.
Right. Yeah. Yeah.
Actually, this is Jian Liang.
Actually, I generate pictures. So, in the campus management, each nodes will join to different programs, so they don't influence each other.
Okay. That was what I was wondering. Okay.
Yeah.
No, but we have 4 nodes, Jan, right? 2 nodes join one program, channel 3, and 2 nodes join channel 10.
No. 4 different channels.
Four different channels.
4 different channels.
No, we have only 2 channels, right? I think.
One in school, one in the home.
Right.
That's four different machines in different residential area, and four machines in the campus for different channels. That's 8.
There's only CCTV 3 and CCTV 10, so there's only 2 channels.
We just report 2 channels here.
Oh, that's right.
Oh, okay.
Okay. All right. Okay, so now I want to move on to the second part of the talk, which does tie in quite a bit to the first part. So as I said before, is after doing this measurement study, we want to take a step back and see if we can understand some of the general principles of these systems and sort of develop a kind of theory that will sort of bring these principles out. So I just want to quickly go through that. So again, the idea is to expose the fundamental characteristics and limitations of P2P streaming systems. And so what in this paper that we recently completed, first we developed a churnless model. That is, a churnless model is when peers do not come and go. They just remain there statically. Then a churn model without buffering. And finally, a churn model with buffering. And I want to cover all 3 of those fairly quickly. So here's the churnless model. You have, say, a server, a source, that's that box up there, and that can stream video or stream out the data at an upload rate of, say, US is the notation we use. The video rate will be denoted by R. So the purpose of this slide here is to just give you the notation. And actually these arrows are wrong here. Each node can upload at some rate UI, so the ith node can upload at rate UI. And each node can download at a rate of DI. Okay, so that's basically the situation. And then, so given that, I just want to ask this little quiz here. Given that you have, and also in the middle, we're assuming that you have abundant bandwidth. There's no problem here that all the bottlenecks are taking place in the access in this model here. And this sort of reflects the situation in the internet today. Now, given that, I ask you, what is the maximum possible streaming rate? If we want to reach out to all, we have n users, and each of these users are going to redistribute video. And think in terms of a fluid model. We're going to move away from the chunks and think in terms of just fluids here. So the chunk sizes are very, very small, and we're going to schedule optimally. What's the maximum possible rate? I've talked to a few of you about this already, so those of you that know the answer, but others that don't, what do you think any ideas what it might be?
This is with buffering or without buffering?
Without buffering. What's the maximum possible rate where you can reach everyone? I'll give you a couple of hints. First hint is that obviously the maximum rate cannot be higher than the rate of the server, right? The server has an upload rate of US. It can only get video out at that speed. There's no way we can reach everyone at a rate higher than that. Do you agree? Another one is that the maximum rate cannot be greater than the minimum of all the download rates. Everyone's downloading at some rate. If we're going to, then you take the minimum guy. You can't get, video faster to that minimum guy faster than his minimum rate, dmin. Right? Now there's a third. These are the 2 sort of most obvious ones. There's a third one that's a little less obvious, though after some thought it becomes fairly obvious as well. Anyone, which ties in all the peers now, aggregates all together. What's another bound that we might have on Rmax?
The upload by
Exactly. So the total rate we have, this is the total upload capacity of the system. This is the upload capacity of the server, and this is the upload capacities of each of the peers, and we add them up. This is the total upload capacity. That's going to be shared among the n peers in the system, the n downloaders. So this is the amount of capacity upload capacity that's available to any one peer, if we split it up equally, is given by this formula here. Okay, so therefore that implies that obviously Rmax must be less than all three of these quantities here, right? And in fact, it can be shown that you can have a scheduling policy that achieves that. So we've just shown that Rmax is less than or equal to this. And what can be shown, a little bit of work, not too much work, that you can construct a scheduling policy that achieves this value here. So that's so in the fluid model, that's the exact value for the maximum streaming rate for one of these peer-to-peer systems is given by this formula here.
Our mutual class doesn't give out this.
Wouldn't be surprised if other independent groups have come up with something similar to this recently. It's a fairly natural thing. Anyway, so next thing is now that's the churnless system. Let's go back to the original model now, where you have peers coming and going. We're going to use this result in the stochastic system where we have peers coming and going. So we have peer churn. And what we're now going to suppose is that there are two classes of peers. One peer, which we call type 1 or ordinary peers, they are, for example, residential access. And we're going to assume that they all have the same rates, upload and download rates. But anyway, residential access. And type 2 peers are super peers, which have campus corporate access, high-speed Ethernet access to the system. All right, in this model. So that's what we're sort of seeing out there. There are in general these two classes of peers. You can extend this model to more than two classes, but I think the case of two classes brings out the essential features of the system. So just a little bit more notation. I've already used this notation. UI will be the upload rate, not for peer I now, but for class I, for a peer in class I. So U1 is the upload rate for, actually this is, I think because I just prepared these talks, this is reversed here. Type 1 is actually the super peers, and type 2 are the ordinary peers. Okay, so keep that in mind. So U1 is the upload rate for the super peer, and has a higher rate than the upload rate for an ordinary peer. So, generally, a peer of campus access is going to have a higher upload rate than the upload rate of a residential peer. And in this model, we'll assume that R, the rate of the video, lies somewhere in between these two rates. Because if R is less than U2, then it's very easy to solve this problem. You can just use a tree-based system to redistribute the video to everyone. All right, so in this stochastic model, we'll assume that new customers, new peers arrive in class I according to a Poisson process with some rate A to I. And the average viewing time have any distribution whatsoever in our model. And denote the average viewing time by 1 over mu I. And then we'll just, this quantity rho I is going to be the ratio of the arrival rate times the average viewing time. So that's rho I. And just a little bit more notation if you'll bear with me. So Li will be the number of type, so now the number of type I peers that are in the system is a random variable because they're coming and going, right? So the number of residential peers that are in the system and the number of campus peers in the system are coming and going. And so that's, and denote that, so denote the number of type I by Li. And what we'll do is we'll naturally assume here that the video rate is less than the minimum download rate. So by making this assumption, obviously if the video rate is greater than the minimum download rate, then there's no way you can reach everyone. So we're going to make this assumption. So that way we don't have to worry about the download rates in this model anymore. Okay, so that's the situation. So first of all, before we get into that, this is Li as a random variable. Here's another question for you guys. Back to school, right? And when you took, stochastic modeling, if you took a course like that, or queuing theory, what is going to be the distribution of Li? I know, given this model here. Again, peers arrive for class I at rate, according to Poisson process with some rate, and they stay in there for some random period of time, general distribution, what's going to be the distribution of that random variable Li? Is it going to be binomial, normal?
Some
No, it's not any of those things, but it's close, right? It's one of the common distributions. It's not normal, because normal could be negative. This Li is always, it's discrete and positive, right? Discrete, non-negative. Poisson, right? Poisson. Because what we have, for each class, we're assuming each class is independent. The rivals from the two different classes are independent. That's very natural. And you have so-called MM infinity Q, right? So basically, customers just arrive, they stay there, and they leave. And the distribution for MM infinity Q is Poisson random variable. Okay? So anyway, so this is a Poisson random variable Li. What's the expected value of Li? The expected number of type I peers in a system. What's that given by? It's a Poisson random variable of what parameter? The parameter rho I. So the expected number of type Li peers in a system is rho I. Okay, so given that, from the churnless theory that we just talked about, we can now ask ourselves at any given time, any given instant of time, will we have so-called universal streaming? By universal streaming means we can reach everyone at the rate R. We can supply everyone video at the rate R. And so at any given time, you'll have universal streaming from that churnless system. This is exactly, if you just go back and apply that churnless system result to this context here, you'll have universal streaming if and only if the number of super peers is greater than or equal to C times the number of residential peers minus U prime, where C and U prime are given by these equations. So it's just a little bit of algebra to get that. You don't need to worry about that. Okay, so then we can ask ourselves then, what's the probability? For what fraction of time do you have universal streaming? For what fraction of time do you reach out to everyone and get the video to everyone? And that's simply the probability of this event here. Okay, so since these are Poisson random variables, you can go ahead and calculate that. It's fairly straightforward. You go ahead and calculate that probability. Again, universal streaming is just, you have universal streaming when you can reach out to all your peers at rate R, when you can feed all your peers at rate R. If you can't feed them all at rate R, we say you don't have universal streaming. Some peers are not getting to see the video at the full rate. Is that clear? Clear? Okay. So that's what we're interested in here. We're interested in calculating the probability or the fraction of time that the system is working, is feeding all the peers in the system at the full rate. Okay, assuming that we're doing this, we're doing this fluid scheduling. So next question is then, so you go ahead and calculate that probability, and that's that's an exercise for a master's student, but we won't bother to do that here. And next question we ask is, what about large systems? P2P systems, we're interested in large systems. What happens when the number of peers becomes very large? So let's let rho 1 and rho 2 approach infinity. So by that means is that we're letting the arrival rates get larger and larger. Rho 1, again, is going to be equal to the expected number of type 1 peers in the system. Rho 2 is the expected number of type 2. We're making those larger and larger, so making the system bigger and bigger. But let's do that in such a way that we hold the ratio at constant. So we have super peers, campus peers, and residential peers, and we're going to increase them, but hold the ratio constant. And in fact, we're going to look at something a little bit more general than that. Basically, we're going to add in this factor here. This is something that statisticians commonly do, something they often do when they look at large systems. And so we're going to do that as well. It's going to help us develop a nice little approximation and give us some insights. So anyway, and then it's not difficult to show because we have this result here that the probability of universal streaming is given by this. So now we're going to look at this probability as rho 1 and rho 2 go to infinity, but they're going to go to infinity in this relationship here. which is a slight generalization of this. And what you can show then is that if this ratio here between the super peers and the ordinary peers is bigger than this constant C. Don't worry too much about that right now. It's not that hard, but here's the constant C. So if that ratio is bigger than the constant C, then you have universal streaming always for a large system, that you can reach out to everyone. You can feed everyone at the video rate of R. If you're below the constant C, if the ratio is less than constant C, then you reach out to no one. You never have universal streaming. You never can reach out to anyone. And finally, if it's exactly equal to the constant C, then you get this expression here where F is the distribution of a standard normal random variable. So what we're seeing here is that there's this critical point that for a large system, in order to get universal streaming, the ratio of the supernodes, the campus nodes, to the residential nodes has to be above this critical value. And the critical value is very intuitive if you think about it. It sounds fancier than it is here. But basically, and if you're below that, then you're not going to get universal streaming at all. So that's basically one thing we're seeing is that in order to get these systems to work, the ratio of the supernodes to the ordinary nodes has to be sufficiently large. If it's not sufficiently large for a large system, and that ratio, if you're above that ratio, things are going to go really well. And if you're a little bit below that ratio, things are going to go poorly. From this result here, we lead to a very simple approximation that's.
So question?
Yeah.
You assume for these two classes, the node join and leave independently?
They join independently.
From your previous statistics.
Good point. Right.
How does it affect the results?
That sometime. Okay. So basically, we're assuming that nodes leave at random, independently of when a program, a movie might start or end. Right. And you're right. That's something to look at in the future is to take into account the fact that many nodes will leave at the same time. Right. That we don't do that here, though.
So
yeah.
My question is that will it affect the C become larger, become smaller, or what do you expect the rate K, the critical value of K, to change?
Well, I think during that program, within the, we saw that a lot of nodes leave every hour. Within that, the number of nodes there may be, fluctuating around because people are just coming and going and leaving because they get tired of the show or whatever, right? And so this theory in many ways would apply in between those hours. Okay, so it's basically one can look at it as a theory that applies between the hours there, and the K value would still, the K value as defined here would still be appropriate. Yeah. Yes.
So in this fluid analysis, is it true that as long as the aggregate upload is larger than the aggregate amount, you have universal streaming?
That's right. That's what's going on. Yeah. Yeah.
This is nice analysis, but I'm wondering if I'm the one who, say, build PPlive,
right,
how this can really help me, because I have no control out of the K out there. And
right.
From my point of view, there's no way to, because the C is actually a parameter that has nothing to do on my side.
Right.
So what would you do?
Excellent question. Right. I have a slide for that at the end of the talk. So let me answer that at the very end, if you don't mind. Okay. So this last result leads to a very nice approximation too, because we said that to calculate the probability of universal streaming, we have that probability of 2 Poisson random variables, which is a fairly messy calculation. But here, for using that result for a large system, you can see that the probability of universal streaming is approximately given by this value for a large system. So we're going to use that in a few seconds here. Now, yeah. Sorry.
I think you addressed my questions. Oh. So actually, I want to ask the question, basically, when the rate isn't large,
right,
what happens? Because I can see the correspondence between the popular and unpopular movie there.
Right.
For the unpopular movie, I mean, you probably have the same row 1 and row 2 for unpopular and popular movie.
Right.
No. I mean, the K is equal. Right. For popular and unpopular movies. But the absolute value for the unpopular movie role is much lower.
Right.
Basically.
Right, that's right.
Compared with popular ones.
That's right.
So I'm interested to know basically how the probability functions change.
Excellent question. 2 slides from here. 2 slides. Okay. So, okay, so we're going to look at examples. 2 examples. Popular and unpopular movie. Okay? So, in this example, we're going to use, these are all just relative rates. So there's the streaming rate, the video rate's 3. Could be, for example, they could represent 300 kilobits per second. The upload, we're going to use an upload rate for the super peer at 7. So it's more than twice the streaming rate, just in this example. It's just one illustrative example. And use the upload rate for an ordinary peer of 1. Okay? So you go through this calculation, and in this case, the critical value of C, that's C value, that K must be bigger than, that row 1 over row 2 must be bigger than, is 1/2 in this case. So we're going to see that 1/2 is an important number here. And used here, because this is, we're going to need to indicate the particular values of mu for the buffering case I'm going to talk about in a second. So typically, the average time that someone watches a video in this model is 30 minutes. And so, and finally, small system, we're going to set the arrival rate of the ordinary peers to 100 rivals per hour, and we're going to vary the arrival rate of the super peers. Okay, and so the average number of ordinary peers in the small system will be 50. And we're going to set the average number of super peers to be vary around 25. And for the large system, we're going to have 5,000 ordinary peers, and the number of super peers is going to fluctuate around 2,500.
Is there any upload rate for the server? We assume it's just going to be as big as
no, it's in there. The upload rate, we're going to vary that. You'll see. We're going to put that. It's also a parameter too. You'll see in the graphs. Good question. All right. So small system. 3 plots here. One is when the upload rate is 7. That is equal to the upload rate of a super peer, and one is 14. So it's twice the upload rate here. Okay. So in this example. And then the third one here is the red one is the approximation that I talked about before. And so what we're seeing here is basically we're plot 1 minus the probability. We're plotting as a function of the arrival rate, really, of the super peers, because that's the only thing that's not fixed. And again, at 0.5 is the critical value here. We're seeing that we're plotting the probability of degraded service, which is 1 minus the probability of universal service. Okay, and we see that as we have more and more super peers arriving, the graded service goes to 0, and if we have relatively few super peers, the probability of degraded service is close to 1. So we're seeing that 1 and 0 phenomenon here, and we're seeing this. This is sort of the critical region here, where we're seeing a probability that's between 0 and 1. So what we're seeing here is this critical region is fairly large. Now, if we go very quickly, we'll come back to this. But if we go to the next slide, this is the large system. Large system now is has many, many more peers in the system, and we're seeing that this critical region now is very pronounced here in the large system. That is that if you're just a little bit lower than the critical value, then the probability of degraded service is very close to 1. And if you're just a little bit bigger than the critical value, then no matter what your server rate is, if it's 7, 70, or 140, you're getting very, very good service here. Okay? And the approximation, of course, in this case turns to be very, very accurate because it's a large system. So this is going to your question here is that this explains one reason why large systems do better than small systems, is because in a large system, this critical region is very narrow. And as long as you operate, a little bit above the critical region, which is 0.5, say at 0.52, critical value is 0.5, as long as you operate a little bit larger than that, you're going to have very good service. Okay? Whereas in the small system, things are much less pronounced, and then so you have to get way above the critical region, like up to 0.76, to get good service. So you need many, many more supernodes. The fraction of supernodes that you need needs to be much larger to get the small system to have performance comparable to the large system. Question back there.
When you talk about universal streaming, it's like this binary state, but it doesn't really seem like that's true. I mean, it seems like if you had 1,000 peers and you were to serve 999 of them well, that would still not be universal streaming.
That's right.
So it seems sort of artificial to make it this sort of binary notion. I mean, to have very good service and you're in this graph and to have terrible service is almost the same thing, is what I'm arguing. Potentially.
Yeah, I guess we could look at another statistic there. I'm not exactly sure what it might be.
Of having the aggregate bandwidth be bigger than the than all of the aggregate
Right.
Which is an interesting thing.
Right.
But I don't think it's like I don't think that this cusp sort of is that interesting. I don't think your system improves that much by making it past that critical point.
Right. That's an interesting point. I'm not sure if I completely agree. Maybe. Let's see. So if you're operating, for example, in this region over here, right? Okay, then it says that the probability of degraded service is very high. That means we can't reach everyone, right? Now, if we look to see also, one could ask the next question is like in this region here, what fraction of users can we reach at the full rate R, and what fraction we can't, right? My guess is that there's a significant fraction that we can't here. But I need to, sit back and think about that for a second.
But
yeah.
It's not clear,
right.
It could be the fraction is very small.
Right.
Potentially.
That's a point to make. Yeah.
Let's discuss this after.
I think the card
Sure. That's a good point. Okay, so let me try to wrap this up then. So one last issue is the next thing is. We saw that PPlive, PPstream, they use buffering. There is definitely buffering going on there, and we see that there's lags as well. That some peers watch the video at different times from other peers. So what if we put buffering into this model that we just talked about? So one important observation here is that the available bandwidth that's available to the system, the available upload bandwidth, right, is varying in time. So this is the available bandwidth here. It comes from that formula that we had before. It's the minimum of the server bandwidth, and this is the aggregate bandwidth divided by the number of peers in the system. And that's fluctuating as the number of ordinary peers and super peers come and leave in the system. And it's so that available bandwidth is fluctuating. So the amount of bandwidth that any one peer can get is fluctuating over time. And just like in traditional streaming systems, client-server streaming systems, when the bandwidth is varying, buffering makes a lot of sense. We all, you look at Real Player, Microsoft Player, they use buffering. That's something that, and one reason you do that is to take into account the bandwidth that's varying. And so we'll do that. We're going to put a buffer at each peer and let the peer buffer up to D seconds of video. And we're going to also have a server buffer. So the server buffer, the server is going to be pumping out at this rate, essentially, fresh content at this rate. And so when that rate is less than R, okay, that means content's coming in at rate R and is pumping out at this rate, which is less than R. That server buffer will accumulate. And then later, when phi of t gets greater than R, that is when the bandwidth of the system exceeds the rate at which we're pumping data in there, then the server will transfer content from the server to the client. Okay? And so in this model, we're going to allow the server to buffer up to D seconds as well. And so to make sure that every peer is going, I think I'll just run through this quickly to give you a general idea, but every peer is going to have a lag of d seconds. And during overflow, there will be times when the server buffer overflows. We're going to drop not from the front of the buffer, but from the, not from the tail of the buffer, but from the head of the buffer. Okay, and finally, just the last point here, like we said, the client lag will always be d seconds in this model, and the client's going to skip if its buffer is 0 and the input rate to the buffer is less than r. All right, so that's it's a very natural buffering model, but here the buffering is buffering at the server and there's buffering at the client. So basically, interaction between a server and one of the peers is as described here. The server will have a certain amount, can buffer up to d seconds, will have a certain amount of video buffered. The client will have the peer will have a certain amount of video buffered. The total amount of video buffered in the server and each of the clients is always going to be a total of d seconds in this situation here. And so that's basically the situation here. So anyway, we can talk about this more afterwards. But results are that the buffering can indeed, and this is something that we see in PPlive, can significantly improve performance here. So we see that the probability of degraded service going from, we have 0 buffer, say, at the critical region here, goes from like 0.5 to 0.4 here in this case here. So, over here, we might be reducing it from 0.3 to 0.2. These kind of improvements that you get are more or less on the same order of the improvements we were getting by increasing the infrastructure, that is, increasing the rate of the server. Okay, and so what one point that we're trying to make here is that you can get by just adding a little bit of buffer, you can get improvements that are often as good, if not better, than what you get by doubling or tripling the rate of your server. In the large system, it's even more pronounced in the critical region. So here's when you have buffering. Here in the critical region here, you might have, when buffering is 0, you have a probability of degraded service equal to 1/2, and it's driven down to like 0.05 when you have the buffering here. And we see here just a little bit of buffering, because all the buffer curves give us basically the same value. In the large system, just a little bit of buffering goes a long way. And these results here were not obtained analytically. These had to be obtained by simulation. We didn't have an analytic solution for that. So, going to your question now. Okay, what can we're coming to the end of the talk. What can PPlive or anything do if row 1 over row 2 is less than C? Right? They don't really, like you said, PPlive can't control that, right? So row 1 and row 2 is the ratio of the number of super peers to ordinary peers. And what if that's less than that critical value C? What can you do? I mean, there's sort of the obvious things. One thing you can do is you can add more infrastructure, that is, increase your server capacity. Build a bigger server farm, right? That can help things a little bit. That won't help too much, though, in a very large system, right? Next thing is you can apply some kind of mission control. You can actually block, if you have some way of determining when a peer arrives what its upload capacity is going to be, and in order to get this ratio in line to what it needs to be, you can block those guys, those ordinary peers, right? Third thing you could use, which was mentioned, is you can use some kind of coding, scalable coding. You can potentially reduce, adapt the transmission rate to the available bandwidth, so you can modify your transmission rate. Or maybe you can give, another thing is think about having some multi-rate stuff where you give lower rate to your ordinary peers and a higher rate to your super peers. And so since the ordinary peers aren't contributing as much, they don't get to see the video at the same rate. So anyway, there's just a lot of interesting questions here, so more research needs to be done in that general area. Yeah?
So I have one suggestion in terms of adding more capacity is to add a small UI change. So when you launch when the user closed the UI, you can detect if the upload and download is if the upload bandwidth exceeds the download bandwidth.
What do you mean by the UI?
The UI when the
UI is like UI here, or does it mean user interface? What is it?
User
interface. Okay.
Yeah. So when a user tries to quit the media player, you just do a simple calculation of the upload bandwidth and download bandwidth. For the residential UI, when you leave, you simply terminate the process. When a corporate or university UI closes, you let the process to go to system tray and require one more step.
I say, well, that's it. Yeah, well, those are good tricks. So next to last, I think last slide actually is some lessons learned from this study is that pure churn causes fluctuations in available bandwidth, similar to, for those of you that worked in networking 5 years ago, or 10 years ago, you remember that a lot of effort was, available bandwidth is changing because of congestion in the internet or congestion in the systems, and we need to do some adaptation for that. These days, there's less congestion in the backbone of the internet, but still we have a very similar problem here because the available bandwidth is varying because of the pure churn. Performance is largely determined by this critical value. Big systems have better performance, as we pointed out. And buffering can dramatically improve things. And the undercapacity region, as we had in the previous slide, needs to be addressed. And with that, I'll just mention one last slide. Important research directions that remain are incentives for uploading content. In this kind of system, one thing I see as a problem with these systems is that it's just very easy for someone to take and not to give. BitTorrent has a wonderful tit-for-tat mechanism that virtually eliminates that free riding problem, but that will not work here. And so that's a major problem here in the future. Another, of course, there's security issues. We can look at attacks on these systems. And there's also the possibility of exploiting these systems for DDoS attacks, just like in file sharing systems. There's, as we talk in one, interesting research area is dealing with that undercapacity region. How, when PPlive or some other company deploys this system on a large scale, and the capacity that's provided by the peers is not sufficient to handle everyone, how are we going to do that? And another interesting research issue is designing these systems, scheduling algorithms, or some other clever mechanism for reducing the lag among the peers, so that there's less lag from when the goal actually happens and when you see the goal. And then with that, I'll just say, thank you very much for all your questions.